1.5 volt source has an internal resistance of 1 ohm. What current must flow through the cell so that its terminal voltage is equivalent to the EMF of the battery? Well, the 1.5 volt source is the EMF, the original sort of rating of the battery we know is called the EMF. Now this little pink dotted line represents the overall battery. It consists of an EMF, the original stamped rating, and an internal resistance inside the battery that we can just imagine as this single little resistor. Now, the little resistor inside of the battery will use up some of that energy. You remember the Kirchhoff's voltage law. When current flows through a complete loop in a circuit, all the voltages across all the resistors in that loop must add up to the total. So within the battery, if there's a tiny little resistance, which is 1 ohm in this case, that little resistor is going to eat up some of that energy. Some of that original EMF is going to get lost inside the battery. So hence the equation when we're calculating terminal voltage. Our terminal voltage is whatever we started with, the EMF of the battery, the 1.5 volts in this case, less whatever is used up within the battery itself. So I'm going to just say less V subscript R, the voltage across the little internal resistor. So when I do my equation, and we recall Ohm's law, V little r is just the total current leaving the battery times the internal resistance of the battery. So there's my equation for terminal voltage. And you can see that the bigger the current, the less there's left over for the terminal voltage. So the terminal voltage gets smaller as the current gets larger, as the battery is working harder. So let's answer the question. What current must flow through the cell so that the terminal voltage is equal to the EMF? Well, we don't want any current to flow. So the only time the terminal voltage is equivalent to the EMF is if the current is equal to 0. In other words, the battery is not working at all. It's not transforming any energy.